Hello everyone, I hope you're doing well. In this video we are going to solve problem 7.1 from Introduction to Statistical Mechanics by Roger Bowley. Let's see the problem statement and then we'll dive into the solution. This is the problem statement. The first one, calculate the single particle density of states in energy of a free particle in two dimensions. We need to calculate density of states expression in energy means in terms of energy. That expression should be in terms of energy because we know that density of states could be expressed in terms of k vector, in terms of omega, in terms of E, and there are the various factors on which density of states depends and can be expressed in. So here we have to particularly express it in terms of energy for a free particle. So if we know what kind of particle we have, for example there is a free particle here, then we can easily find out the density of states expression in terms of energy, for example here in two dimensions. So we need to consider the two-dimensional case. Now let's see how to solve the problem. I recommend you all to go through the topics of this chapter. This is related to Maxwell distribution of molecular speeds, and the theory here is very clear and it makes your solution process very easy. I have already uploaded some of the videos on the topics in which we derived and understood the concept of density of states in 3D, 2D and 1D, and it helps you a lot in solving the problem because mostly in exams you are given unseen problems. So you should be familiar with the topics, with the basic concepts, and that makes your solution, your problem solving capabilities richer, and it just makes your process easy because I want you people to be independent and just watch that video as a last option or as a confirmation that whether the method you are using, or for example the formulas you are using, or the expression you resulted is correct or not. Because I myself believe that we should focus on our capabilities related to how how well and how early we can find solutions to the problems. So let's see. We need to calculate density of states in energy, which means d of E. D as a function of E needs to be calculated for a free particle. We know that the energy of a free particle is h cut square k square by 2m. Here k is the wave vector. Okay, this is the expression of energy for a free particle, and we have two-dimensional case. So the formula that we'll be using is, we know that density of states in energy is given by, in brackets we'll see two dimension. Okay, this is given by this expression. This is basically d of k dk by de. Okay, d of k is the density of states formula in two dimension. I have mentioned here the three formulas for the for all these dimensions. In 3D we have d of k equals to this. Okay, vk square 2 pi square, v is the volume. In 1D we have L by pi, where L is the length of the system, and d of k equals ak by 2 pi, where a is the area of the system under study. And this is the formula that I will be using because we have the 2D case. You should know these formulas and it will make your the whole process way easier. Now we need to calculate dk by de, and we can calculate it from this energy expression. Let us call this formula as equation number 1. Now we have E equals h cut square k square by 2m. Okay, de derivating both sides with respect to k. So d by dk will be applied on h cut square k square over 2m. Sorry, h cut square by 2m is a constant quantity, so it will come out of the operator, and if the operator is simply applied on k square, and the derivative of k square is 2k. This 2 and 2 cancels out, and we are left with h cut square k by m. Okay, dE by dk is h cut square k by m, while we need dk by dE, not dE by dk, so we'll take inverse, and hence we'll get the value of dk by dE by taking inverse. So m will be in numerator now, and the above term will be in denominator. Now we'll put this value right into expression 1. Put in 1, which is d of e equals ak by 2 pi dk by dE, which is m by h cut square k. K and k cancels out, and we are left with am by 2 pi h cut square. And we can see here the density of states in terms of energy is independent of energy itself. So it's a constant quantity. A is the area of the system, and it's a constant quantity. M is constant. All of these things are constant, and energy expression doesn't appear here. So in 2D case, density of states and energy is independent of energy, or you can see here, and that is the final formula, and that was the answer. Now let's see the other problems also, and you can check all the solutions to all of these problems in statistical mechanics playlist, where I have added all of these problems, and there are solutions to other problems as well from other chapters. So stay tuned, keep watching. Good luck for your exams.